Download this code from codegive.com, link in the description below. Buffer overflow exploitation and detection with AppCheck NG, a deep dive. This tutorial provides a comprehensive understanding of buffer overflows, their exploitation techniques, and how AppCheck NG can be used to detect and mitigate them. We will cover the following topics. 1. Introduction to buffer overflows ***. What is a buffer overflow? Different types of buffer overflows. Why are buffer overflows dangerous? 2. Understanding memory layout and call stack ***. Stack structure. Heap structure. The importance of understanding these structures for exploitation. 3. Basic buffer overflow exploitation ***. Exploiting stack-based buffer overflows. Overwriting the return address. Shellcode introduction and execution. Code example in C/C++ with vulnerable code. 4. Advanced buffer overflow techniques ***. NOP sleds. Return to libc, RET to libc. Return-oriented programming, ROP. 5. Introduction to AppCheck NG ***. What is AppCheck NG? How AppCheck NG works. Key features and benefits. 6. Detecting buffer overflows with AppCheck NG ***. Configuring AppCheck NG for buffer overflow detection. Static analysis capabilities. Dynamic analysis capabilities. Using AppCheck NG to identify vulnerable code. 7. Mitigating buffer overflows ***. Safe coding practices. Compiler-based defenses, example stack canaries, ASLR, DEP. Using AppCheck NG to enforce secure coding standards. 8. Code example with AppCheck NG integration ***. Vulnerable C/C++ code. Analysis using AppCheck NG. Fixing the vulnerability based on AppCheck NG findings. 9. Conclusion and further learning resources ***. Let's begin. 1. Introduction to buffer overflows ***. A buffer overflow occurs when a program writes data beyond the allocated memory region for a buffer. This can overwrite adjacent memory locations, potentially leading to unpredictable program behavior, crashes, or, most dangerously, the execution of malicious code. Different types of buffer overflows ***. Stack-based buffer overflow * occurs when a buffer allocated on the stack is overflowed. The stack is a LIFO, last in, first out, data structure used for function calls and local variable storage. Exploiting stack overflows often involves overwriting the function's return address to redirect execution flow. Heap-based buffer overflow * occurs when a buffer allocated on the heap is overflowed. The heap is a region of memory used for dynamic memory allocation, using functions like malloc and new. Heap overflows can corrupt heap metadata, leading to memory corruption and potentially arbitrary code execution. Integer overflow / underflow * while not strictly a buffer overflow, integer overflows can lead to them. If an integer used to calculate the size of a buffer overflows, it can result in a smaller than expected allocation, making subsequent writes vulnerable. Why are buffer overflows dangerous? Buffer overflows are particularly dangerous because they allow attackers to execute arbitrary code *. The most severe consequence is the ability to inject and execute malicious code, shellcode, by overwriting the return address or other critical data structures in memory. Gain control of the system * by executing shellcode, an attacker can gain control of the target system with the privileges of the vulnerable process. Cause denial of service. DOS overflowing a buffer can lead to crashes and program instability, causing a DOS. Modify data. Overwriting data can corrupt sensitive information, leading to data breaches or incorrect program behavior. 2. Understanding memory layout and call stack. Understanding the memory layout is crucial for exploiting buffer overflows. Here's a simplified overview. Text segment, code contains the executable instructions of the program. Typically read-only to prevent modification. Data segment. Contains initialized global and static variables. BSS segment. Contains uninitialized global and static variables. These are initialized to 0 by the operating system when the program starts. Heap. Used for dynamic memory allocation during program execution. Stack. Used for function calls, local variables, and return addresses. It grows downwards, from higher to lower memory addresses. The stack structure. The stack is organized into stack frames, one for each active function call. A stack frame typically contains local variables. Variables declared within the function. Function arguments. Values passed to the function. Return address. The address in the calling function to which execution should return after the function completes. Saved frame pointer, EBP or RBP, a pointer to the previous stack frame's base pointer. Used for navigating the stack. Saved registers. The values of any registers that the function modifies. The heap structure. The heap is a region of memory managed by the operating system's dynamic memory allocator. It contains blocks of memory that are allocated and freed as needed by the program. Heap metadata, example, the size of allocated blocks, is stored alongside the allocated blocks. Corrupting this metadata can lead to vulnerabilities. 3. Basic buffer overflow exploitation. Let's focus on exploiting a stack-based buffer overflow. Overwriting the return address. The key idea is to overflow a buffer on the stack and overwrite the return address with the address of our shellcode. When the function returns, instead of returning to the expected address, it will jump to our shellcode, giving us control. Shellcode introduction and execution. Shellcode is a small piece of assembly code that performs a specific task, usually spawning a shell. It is carefully crafted to be position independent and to avoid null bytes, which can prematurely terminate strings. Code example, vulnerable C code. Explanation. Vulnerable function takes user input as a string. It declares a buffer of size 10 on the stack, char buffer 10. strcpy is used to copy the user input into the buffer. strcpy does not perform any bounds checking. This is the vulnerability. If the input string is longer than 9 characters, plus the null terminator, strcpy will write beyond the bounds of the buffer, overwriting adjacent memory on the stack. Exploiting the vulnerability, conceptual. 1. Craft an input. The input string needs to be longer than 10 characters. 2. Determine the offset. You need to determine how many bytes of padding are needed before you start overwriting the return address. This can be done through trial and error using a debugger like GDB. We usually fill the buffer with a pattern, example AAAA, BBBB, etc. 3. Shellcode. Choose or write the shellcode you want to execute. A simple shellcode for Linux might spawn a shell. Shellcode writing is a complex topic in itself and requires assembly knowledge. For return address *, find the memory address where your shellcode is located. This could be in an environment variable or in the program's address space if you can place it there. The return address needs to be packed into the appropriate format, example little-endian on x86. 5. Combine and execute *, construct the input string, padding return address shellcode. 6. Run the program with the crafted input. Example, simplified attack. Let's assume the following. These values will vary depending on the system and compiler. * padding needed, 12 bytes, this means the return address is 12 bytes away from the start of the buffer. * shellcode address, 0xbffff000, this is a hypothetical address where our shellcode is placed. You'd need to find this address in practice. Remember, addresses are architecture dependent and will most likely be different for a 64-bit system. *shellcode, let's represent the shellcode simply as shellcode_bytes, in reality this would be a sequence of machine instructions. Then the attack string would look something like this, expressed conceptually. AAAAAOB plus \xf0 \xf0 \xff xbf plus shellcode_bytes. *AAAAOB, the 12 bytes of padding. *x00 \xf0 \xff xbf, the shellcode address, 0xbffff000, in little-endian format. * shellcode_bytes, the actual shellcode. Important notes. Security measures. Modern operating systems and compilers have security measures like address space layout randomization, ASLR, and data execution prevention, DEP, that make buffer overflow exploitation more difficult. ASLR randomizes the memory addresses, making it hard to predict where the shellcode will be located. DEP prevents code execution from data segments like the stack. You may need to disable these features, which is generally not recommended in a real-world environment, to successfully exploit this basic example. *debugger, GDB. Using a debugger like GDB is essential for analyzing the program's memory layout, finding the return address offset, and verifying the shellcode address. Shellcode generation. Shellcode is typically written in assembly language. Tools like misvenom, from the Metasploit framework, can be used to generate shellcode for various architectures and operating systems. This example is for educational purposes only. Exploiting vulnerabilities without authorization is illegal and unethical. 4. Advanced buffer overflow techniques. NOP sleds. A sequence of NOP, no operation, instructions. If the exact address of the shellcode is uncertain due to ASLR, a NOP sled is placed before the shellcode. The return address can point anywhere within the NOP sled, and the execution will slide down to the shellcode. Return to libc. ret2libc exploits a program without directly injecting shellcode. Instead, it chains together calls to existing functions in the C standard library, libc, to achieve the desired effect. Example, calling system/bin/sh to spawn a shell. ret2libc is useful when DEP is enabled. Return-oriented programming, ROP, a more general technique than ret2libc. It involves chaining together small snippets of code, gadgets, that end with a ret instruction. By carefully selecting and chaining these gadgets, an attacker can perform complex operations without injecting new code. ROP is used to bypass both ASLR and DEP. 5. Introduction to AppCheck. AppCheck NG is a next-generation application security testing platform that combines static and dynamic analysis to identify security vulnerabilities in applications. It helps developers and security professionals find and fix bugs early in the development life cycle. How AppCheck NG works ** static analysis * AppCheck NG analyzes the source code without executing it. It uses techniques like data flow analysis, control flow analysis, and symbolic execution to identify potential vulnerabilities. Dynamic analysis * AppCheck NG executes the application and monitors its behavior for security flaws. It can use techniques like fuzzing, taint analysis, and memory corruption detection. Integration * AppCheck NG integrates with various development tools and environments, such as IDEs, build systems, and CI/CD pipelines. Key features and benefits * comprehensive vulnerability detection * identifies a wide range of vulnerabilities, including buffer overflows, SQL injection, cross-site scripting, XSS, and more. Precise results * minimizes false positives and provides detailed information about detected vulnerabilities, including their location in the code and potential impact. Actionable recommendations * offers practical guidance on how to fix vulnerabilities and improve the security of the application. Continuous security * integrates with the development life cycle to provide continuous security testing and monitoring. Compliance * helps organizations comply with security standards and regulations. 6. Detecting buffer overflows with AppCheck NG ***. AppCheck NG provides several ways to detect buffer overflows. Static analysis * code inspection * it analyzes the code for unsafe functions like strcpy, gets, sprintf, etc., that are known to be prone to buffer overflows. Data flow analysis * it tracks the flow of data through the program to identify potential buffer overflows. For example, it can detect if a user-supplied input is being copied into a fixed-size buffer without proper bounds checking. Symbolic execution * it explores all possible execution paths of the program to identify potential buffer overflows. Dynamic analysis * fuzzing * AppCheck NG can generate a large number of random or semi-random inputs and feed them to the application. This can help uncover buffer overflows that are not easily found through static analysis. Taint analysis * tracks user-controlled data as it flows through the application. If tainted data is used in a way that could lead to a buffer overflow, AppCheck NG will flag it as a potential vulnerability. Memory corruption detection * monitors the application's memory usage for signs of corruption, such as writing beyond the bounds of allocated buffers. Configuring AppCheck NG for buffer overflow detection *. The specific steps for configuring AppCheck NG depend on the product and your development environment. Generally, you will 1. Install and configure AppCheck NG * follow the installation instructions provided by the vendor. 2. Integrate with your build system or IDE * configure AppCheck NG to analyze your code automatically during builds or when you save changes. 3. Set up rules and policies * configure AppCheck NG to focus on buffer overflow detection. This might involve enabling specific rules related to dangerous functions or memory safety checks. 4. Run analysis * initiate a static or dynamic analysis scan of your code. 5. Review results * examine the reports generated by AppCheck NG to identify potential buffer overflow vulnerabilities. 7. Mitigating buffer overflows ***. Safe coding practices *. Avoid unsafe functions. Do not use functions like strcpy, gets, sprintf. Use their safer alternatives, such as strncpy, fgets, tinprintf, which take a size argument to limit the number of bytes written. Bounds checking. Always validate the size of user input before copying it into a buffer. Ensure that the input is smaller than the buffer size. Input validation. Validate user input to ensure that it conforms to expected formats and values. Use memory-safe languages. Consider using languages like Java, C, or Python, which have built-in memory management and prevent buffer overflows. Although even in these languages, vulnerabilities related to input sanitization and logic can still exist. Compiler-based defenses. Stack canaries. A random value placed on the stack before the return address. Before returning from a function, the canary is checked. If it has been modified, it indicates a buffer overflow, and the program terminates. Address space layout randomization. ASLR randomizes the memory addresses of the program's code, data, and stack. This makes it difficult for attackers to predict the location of shellcode or other critical data. Data execution prevention, DEP, /no execute, NX marks certain memory regions as non-executable, preventing the execution of code from data segments like the stack. Using AppCheck NG to enforce secure coding standards. Custom rules. Configure AppCheck NG to enforce specific coding standards that prohibit the use of unsafe functions and require proper bounds checking. Automated code reviews. Integrate AppCheck NG into the code review process to automatically identify violations of secure coding standards. Training. Use AppCheck NG's findings to educate developers about buffer overflows and secure coding practices. 8. Code example with AppCheck NG integration. Vulnerable C code, same as before. Analysis using AppCheck NG, illustrative. 1. Run static analysis. After integrating the code into AppCheck NG, running a static analysis scan should flag the use of strcpy in vulnerable_function as a high-severity vulnerability. The tool would likely provide a message similar to, strcpy is an unsafe function that can lead to buffer overflows. Use strncpy instead. 2. Run dynamic analysis, optional if you set up fuzzing or taint analysis within AppCheck NG. It might automatically generate inputs that trigger the buffer overflow and cause a crash. This would provide further evidence of the vulnerability. Fixing the vulnerability based on AppCheck NG findings. Based on the AppCheck NG analysis, we replace strcpy with strncpy and add bounds checking. Explanation of the fix. strncpy. We replaced strcpy with strncpy, which takes a size argument. This prevents writing beyond the allocated buffer size. Size of buffer 1. We pass size of buffer 1 to strncpy to ensure that there is always room for a null terminator. Buffer size of buffer 1 equals \0. We explicitly null terminate the buffer after the copy. strncpy doesn't always null terminate if the source string is larger than or equal to the size argument. Bounds check. We added a check to make sure the input is not larger than the buffer. If it is, we print an error message instead of overflowing the buffer. After fixing the code, you can rerun AppCheck NG's analysis to verify that the vulnerability has been resolved. The tool should no longer flag the strncpy usage as a high-severity issue. It is important to understand that the goal is to find and fix code smells early. 9. Conclusion and further learning resources ***. Buffer overflows are a serious security threat that can lead to severe consequences. Understanding how they work and how to detect and prevent them is essential for building secure applications. AppCheck NG is a powerful tool that can help you identify and mitigate buffer overflows early in the development life cycle. Remember to practice secure coding practices, use compiler-based defenses, and integrate security testing tools into your development process. Further learning resources *OWASP, Open Web Application Security Project https://owasp.org/ https://owasp.org *SENS Institute https://www.sens.org/ https://www.sens.org *exploitDB https://www.exploitdb.com/ https://www.exploit-db.com *books *Hacking, The Art of Exploitation by John Erickson *The Shellcoder's Handbook by Chris Onley et al. *Grey Hat Hacking, The Ethical Hacker's Handbook by Alan Harper et al. *Online Courses Coursera, edX, Udemy often have courses on cybersecurity and reverse engineering that cover buffer overflows. This tutorial provides a solid foundation for understanding buffer overflows and using AppCheck NG to detect and prevent them. By continuously learning and practicing secure coding techniques, you can significantly reduce the risk of buffer overflow vulnerabilities in your applications. Remember to always test and analyze your code to ensure that it is secure. Good luck.